is Dhrumil. Dhrumil is a PhD student in computer science. And that's also about our work on quantum computing, quantum algorithms for semidefinite programs.
Yeah, so good afternoon, everyone. Am I audible? So today we're talking about quantum algorithms for semidefinite programming, and specifically variational quantum algorithms. So here, and this was a paper, last year we worked on this paper with Patrick Chikos and Mark. And there are two essential ingredients for this paper. The first one is the variational quantum algorithm, and the second one is an SDP, semi-definite programming, which I think everyone knows it, but still I will briefly go over both of this. And then we'll go into the actual algorithms. So let's get started. So what are semi-definite programs?
Yes, not sharing your slides.
Dhrumil and I have a bet that there will be no typos in this talk. Go on slide 1. That should be capital.
Is it not showing up? Okay.
Share it.
No, it is we're sharing the
PowerPoint.
Okay. So in general, the semi-definite programs look like this, like where you have some maximization or minimization, and there is an objective function, and you have constraints. In the constraints, this is a linear map, and X is the positive semi-definite variable over which you have to do the optimization, and B is a matrix with constants. Okay, so this is known as a primal form of SDPs, and just like the linear programming, we have a duality in SDPs too. So if you so this is a dual program. So if your primal program is like a maximization is a maximization problem, then a dual program will be a minimization, and the phi dagger is just the adjoint map of the original map, and D star and P star are the optimal values. So this is a general form of SDPs. Like most of the optimization problems that you encounter in quantum information theory, you can cast them as any one of the problems. But an interesting thing is there is a standard form of SDPs where instead of phi of X, you replace the phi of X with this matrix, and B you replace with this matrix. This is a very specific case of an SDP. And why is this useful? Because this type of expression comes a lot in computer science in combinatorial optimization problems. And so studying this specific problem is also very important. Now, classically, we all know that we can solve an SDP in a bilinear time. Bilinear, I mean N is a dimension of the input matrices. Input matrices are C, A1 to AM. These are the input matrices. And the size of the input matrices is N. And M is the number of constraints that the SDP has. So classically, we can solve an SDP in this bilinear NM time. So the question is, what can we do in a quantum case? Now, just imagine that your N is quite large, okay, like exponential, very high. Then it's very hard to compute the gradient. Like whenever you do this kind of, whenever you try to solve an SDP, you have to compute gradient or Hessian or any higher order derivatives to actually compute to go towards the optimal value. But if you have this N is quite large, then it's very hard to compute that. Okay, so we'll address those questions here. So this is just a brief overview of the SDPs. Now, there are fault-tolerant quantum algorithms for SDPs. Like it started in 2016 by the paper by Fernando Brandao. This was the first paper where they proposed a quadratic speedup. So instead of NM, they proposed the root of NM. Okay, but the lower bound is something different. The lower bound is root of N plus root of M. It's a plus, it's not a multiplication. And it was proved in the last paper, this one. So these are the main papers that were dealing with quantum algorithms for SDPs. But the main problem is that it's a fault-tolerant quantum algorithms. So if you, for realizing this algorithms, you need a fault tolerant quantum computer. So the question is like, we have this NIST devices. By NIST, I mean it's noisy intermediate scale quantum devices. Okay. So is it possible to use those NIST devices and solve SDPs? So that's the question we try to address. Now, before going into the actual algorithm, I explained the first ingredient. This is the second ingredient, variational quantum algorithms. Okay, so I'll just give a brief overview of that. This is a rough sketch that I made. Okay, so let's say your objective function is pretty simple. Objective function. You're trying to minimize an expectation value of an Hermitian operator with respect to some quantum state, and that quantum state is actually parameterized in some way. What do I mean by parameterized? Means that there is a quantum circuit that prepares the state, and you try to measure something, and this is the expectation value that you get. Okay, so there are two components in a variational quantum algorithm. The first one is a quantum circuit that prepares the state and estimates the expectation value. And the second thing, this is a controller, which is a classical optimizer, and there is a feedback loop going on in order to solve this optimization problem. And the classical optimizer, if you want to estimate the expectation value, you can use the quantum circuit. If you want to estimate the gradient of this expectation value with respect to this theta vector, that also you can do with a quantum circuit. I will explain next how you can do it. And this loop, like you estimate, then you update the parameters by estimating the gradient, and you change the parameters, you again estimate, and this is how it goes on until you find the optimal value. So this is a variational quantum. This is the framework of the variational quantum algorithms. Now the objective function can change, but in general, the objective function needs to have some kind of expectation value of Hermitian operator so that you can estimate, you can use quantum circuits to estimate this. Okay. Now, important question is how to evaluate gradients. So there is this rule known as parameter shift rule. You can evaluate gradients, Hessians, and higher order derivatives using this rule. And let's take a simple example. The example that was given before, where there was a simple expression of expectation value. Now I want to calculate the partial derivative of that expectation value with respect to theta I. So initially there were like theta 1 to theta 6. So let's say I want to evaluate with respect to theta 3. Okay. So it's exactly equal to, make sure it's not approximation, it's exactly equal to the expectation value evaluated with this shifted parameters. So that's the beauty of it. You can use the quantum circuits that was given before to evaluate the gradients and Hessians and higher order. This is a parameter shift rule.
Right, let me interrupt. You should probably clarify that this follows from the assumption in the ansatz, right? Those are like rotation operators.
Yeah, like right? Those are like trigonometric quantities, and that's why it follows. Yeah. It's specific to quantum circuits. It's not like so after like going over the ingredients like variational quantum algorithms and the SDPs, I'll just give a brief overview of all the algorithms. There is a connection between all the algorithms. So in the paper, we give 3 algorithms. The first algorithm is for the general form of SDPs. The second algorithm is for the equality constraint standard form. So remember, there was a standard form. I wrote it on this side of the slide. So if your constraints are all the equality constraints, then it's known as an equality constraint SDP. And the another one is inequality constraint SDP. So we give 3 quantum algorithms, but I will just give a brief sketch of all the algorithms. So just to get started. So initially we have the constraint form of an SDP. So, and using that, what do you mean by the constraint form? Constraint form is like, you have an objective function, you have some constraints and everything. That's a constraint form. You have to use some techniques that we have in the paper to convert to an unconstrained form with no constraints at all. And you just have objective function, that's it. And you're trying to minimize or maximize. And this unconstrained form sort of behaves like a mini-max kind of a thing. Initially, let's say this was just a max SDP, but when you arrive at the constraint form, because you try to get the constraints and put in the objective function, it somehow becomes a mini-max kind of a game. Okay, and this unconstrained form is essentially, you can express in terms of the expectation value of input Hermitian matrices. And that's where we can use variational quantum algorithm. And you actually parameterize. By parameterized form, I mean that you express in terms of the quantum circuit parameters. That's what I mean by parameterized form. And once you get the parameterized form, you use any classical optimization method. We used a gradient-based methods, and we can evaluate the gradient using the parameter. So this is just a brief overview of how the algorithms work. Now instead of, I won't be talking about all the three, I'll just briefly talk about the first two algorithms. So we'll talk about the general form of SDPs. So this is a general form where you have an objective function, you have constraints, and using some techniques, we arrive at this minimax kind of a thing, okay? Where rho is essentially lambda, so basically X is basically lambda into rho. Okay, X is a positive semidefinite matrix, and you can write, and rho is also a positive semidefinite matrix, so you can write in terms X is lambda into rho. And similarly, we converted like mu and sigma and like that. Now, what are this theta 1, theta 2, and theta, all this stuff? So we need to prepare two states to essentially estimate the expectation value. This is also an expectation value, this is also an expectation value, this is also an expectation value. So we need to prepare quantum circuits. So with respect to rho, all the parameters of the quantum circuits is denoted by theta 1. For preparing sigma, the quantum circuit parameters are denoted by theta 2, and so on. So there are essentially two quantum circuits that are fighting against each other in order to win. Okay. I think the figure will make it more clear. Yeah.
So I have a quick question. Where did the theta come from on the last one?
No,
Because on the first 2 lines there was no theta, and then there was a theta on the last.
This one?
Yeah.
Yeah. So we have two quantum states, right? So we need to prepare those quantum states.
One theta.
For preparing the quantum states, you need a quantum circuit. And theta 1 is the parameters, it's a vector.
Okay,
It's like all
It's
the,
the one that.
Yeah.
The,
That prepares
parameter
rho.
that enters into the J.
Yeah.
That prepares the rho.
Yeah. And similarly, there is a quantum circuit parameters with theta 2, it prepares sigma.
You should probably call the P star on the last line like P star prime.
No, we have an assumption that it's faithful.
I see. You're allowing an optimization over all states.
No. It's a subspace, but there is an assumption, and it's very common in variational quantum algorithms. We assume that the cost function is faithful, which means the global optimal point lies in that subspace.
Okay.
Yeah, so it's fine. Okay. So these are the two quantum circuits which are like fighting against each other. And there was a minimax game. So what the first step that we will do is maximize the objective function. This G, I didn't have the space to write the whole thing. So this G is essentially this cost function. Okay. So we maximize with respect to theta 1 and lambda, and we'll check if it's converged or not. If converged, then you update the other two parameters, right? And it will go on and on. And whenever you have to evaluate the gradient and get the gradient information, you'll use the quantum circuits here. And that's how the algorithm will go on. We didn't prove the convergence for this algorithm, but for the next algorithm, we give a convergence rate, like at what rate it will converge to a global optimal point. This was like pretty, we tried, but it was not able to work. We didn't try to like, so okay. Now for the equality constraint SDPs, this is the primal form. Similarly, we convert to an unconstrained form first, and from the unconstrained form, we convert to a parameterized form, where we just have one quantum state, this rho, and if you need to parameterize it, we just need to have this theta, and that's it. And the rest is the same. And this is algorithm. Now, instead of two quantum circuits, we'll just have one quantum circuit that will prepare rho and estimate the expectation value. And this is the overall circuit that we'll have. Now, the simulations is like for the BQHGF is the variational quantum algorithm for the general form. And we check the convergence on the max cut instances. like we randomly generated visible max instances and we try to see if it's converging. We didn't check the speed, we didn't compare it with anything, just saw whether it's converging or not. And we took two cases. The one is a noiseless case and the noiseless simulator, and the second one is a noisy. The noisy is this quantum simulator. It mimics an actual quantum device. And for both the cases, we saw that it's converging pretty nicely. And for the second algorithm, the same thing. And for the third algorithm, also the same thing. So this was a punchline. Noise reason. Okay. And for the conclusion, we proposed variational quantum algorithm for 3 different types of SDPs. And the thing that I didn't explain here is that we also prove a convergence rate for one of the algorithms. And we provide numerical evidence that it actually works in practice when you actually simulate on a real quantum. So that's it. Thank you.
Very nice talk. You have to answer questions.
Oh, sir.
So, Arshad?
Dhrumil, thank you for the clear talk. Can you go back to the slide where you show solutions to SDP? If you had to, if you go to one, the one on the back. Yeah.
This one?
One more. One more slide to the back. To the back.
To the back.
Yes.
Yeah.
If you were to start from the first line, is that not enough to do the computations? Is that why you're going to the second and the third line?
So for the first one, we have constraints, right? So we need an equivalent form, an unconstrained form, so that we are just focused on the objective function, and we can use gradient descent or that kind of methods. We won't be using gradient descent because there is another method which is known as a dual ascent, where you actually descend on the dual and ascent on the primal variable. So these are like primal and dual variables kind of a thing. Okay, and you just have an objective function that you just need to take care of. And the beautiful thing is that the optimal value for this kind of expression is the same as the optimal value of the original.
Right.
So that's what we want. That's it.
And the difference is you cannot use the gradient descent in the first one. You can use it.
Yeah, we need to check every time. We need an oracle to actually check every time whether it's we are actually satisfying the constraints or not. It's better to just do it in this way.
Thanks for
Is this related to the way you put in Lagrange multipliers when you have
Yeah.
put in
But this is not just in Lagrange multipliers. We have just a linear penalty. We have a quadratic penalty too here. So yeah, it's very simple. You're right. Any other questions?
Can you go to your very last plots?
Yeah.
So the QASM, are you simulating on Qiskit?
Yeah. We actually use penny lines. This is all the Python. There is a lot of Python libraries, and at the back end we use the quantum simulator of Qiskit, so we can integrate that.
Have you tried to do anything with the actual idea?
I didn't try it, but they claim that the quantum simulator is actually the same. It mimics the same thing.
Yeah.
We kind of
We found differences.
Yeah, we can try it.
We can
It
do
would
it.
be interesting to try.
What, which device were you using that's actually simulate, like, when you do the noisy simulations, it's actually simulating some device. Do you know the name of the device?
For-
and how many
for what?
qubits
For the noisy?
Qiskit, for the noisy one.
Quantum.
Yeah, but like IBM and some random city in the world, right?
It's IBM Q something and then in brackets Q.
I think there is a default machine that it mimics. I don't know which default one it is. So if you just say CHASM, it picks a default machine.
Okay.
But it's using at least 16 and 32 qubits, or that's the dimension.
That's not the dimension.
So
Yeah,
4
that's the
qubits
dimension of the
and 5
input matrices. Yeah. So for the max cut, these two are the number of vertices of a graph. Yes. So that's it.
How much of a deviation did you find between the simulator and the actual device?
I don't remember, but it was significant.
Really? How long ago did you do that?
Depending on the number of qubits.
How long ago did you do that?
Less than a year?
Okay.
I like I tried to do it, but there was a lot of wait time.
Yeah,
I
that's
was
the
even
problem.
frustrated. And I was
Yeah.
like,
Talk about that.
Okay.
We might be able to talk about stuff.
Ah, thanks.
Do you have a question?
All right, we should move on. I think we're kind of past the time. Thank you again.